Hello students and welcome to Chemistry at JP's Academy, and I'm Nitin sir. In today's one short lecture, we are going to do a very important chapter which is polymers. Students, this chapter is very important from your boards as well as entrance exams perspective. We're going to study the chapter in detail. We will start by understanding what exactly are polymers, what is the process of polymerization, how we classify polymers. We will then do the preparation of some important polymers. Finally, we study something called as the degree of polymerization. So, before I start the lecture, students, I request everyone to please like the video and subscribe to the channel. Let's start. Students, what exactly are polymers? Now, the word poly means many, mer means unit. So, many units which combine together to form a large molecular mass compound is called as a polymer. So, they are high molecular mass substances containing repeating units which combine together to form polymers, which are also called as macromolecules. Now, this process of going from monomers to macromolecule is also called as polymerization. Let's classify polymers. Polymers are classified on the basis of their origin or their source, whether they are naturally obtained or they are made in lab. Then monomers involved, are there single monomers or are there multiple different monomers in a single unit? The structure, are they elastic, are they fibrous, or do they soften on heating? We will study all this in detail. However, I'm just giving you an overview. On the basis of molecular forces, is the strength strong between the bonding molecules? And finally, the process of synthesis, addition, polymerization, condensation, how are they obtained? We also understand free radical mechanism in this. Now let's start, students, with the first classification, which is based on the origin or source. Now, natural polymers, as the name suggests, polymers which are found in nature, mostly obtained from plants and animals. Wool can be an example. For example, we have natural rubber, which is a polymer of isoprene. Nucleic acid, students, such as DNA and RNA. Proteins are also polymers of amino acids, and polysaccharides such as starch and glucose are polymers, are natural polymers. Semi-synthetic polymers, students, semi-synthetic, for example, if we consider, let's say, something like cotton, we use that to make clothes, but however you have to process that. So part of it is obtained from nature, part of it is synthetically modified in the lab. Such are called as semi-synthetic polymers. So these are derived from nature, but we carry out some chemical modification. I've given some examples. And similarly, synthetic polymers. Synthetic polymers are those polymers which are made 100% only in labs. Now, students, these examples are very important because in your respective exams, you can have questions where they would give you polymers and probably they would ask you to classify them on the basis of their origin or source. Next, students, we have on the basis of monomer involved. So when I say monomer, the classification is homomer. Now, as the name suggests, homomer, homo means a single unit. So polymers from only one kind of monomer is called as a homomer. A common example here will be preparation of polythene, in which the only monomer unit involved is ethene or ethylene, which on the process of polymerization becomes polythene. However, if we consider a copolymer or a mixed polymer, an example over here is a rubber polymer, which goes by the name Buna-S. I'll explain what that means. So the monomer units involved are styrene and butadiene. The Bu comes from butadiene. Na is your catalyst, or you can also say the initiator. S is from styrene, and hence the name Buna-S, which is, students, a rubber polymer. So here we have polymers having more than one repeating unit. Next, students' classification is on the basis of structure. The first classification is linear polymers or linear structures. As the name suggests, polymers in which the monomer units form long straight chains are called as linear polymers. Now they have high density, high tensile strength and high melting point. Some common examples we have over here is polythene, nylon and polyester. Branched means along with linear structure you'll have some branches in between. However, students, because of these branches, what happens is these polymers have low density, poor packing, low tensile strength and low melting points when you compare them with linear polymers. For example, amylopectin and glycogen. Next, we have cross-linked polymers. Polymers which have 3D network structures. These are cross-linked polymers. They are hard, rigid and brittle due to the cross networking. For example, vulcanized rubber, bakelite, epoxy resins, melamine, etc. The next classification is on the basis of molecular forces. The first example in that is elastomers. As the name suggests, elastomers will have high degree of elasticity. You can apply force and pull them apart. However, when you release the force, all the molecules will come back to their original position. When stretching force is removed, molecular chain of elastomers do not remain extended and aligned. They return to their original configuration. When you compare their intermolecular forces with that of fibers, intermolecular forces required to hold them are weaker when you compare that with fibers. Occasional cross-linking is also required to avoid the slipping of molecules. Some common examples will be styrene butadiene rubber, which is Buna-S, which we just did, Buna-N and Neoprene. All the three examples are examples of rubber polymer. Next, we have fibers. As the name suggests, they are the opposite, you can say opposite of elastomers. They do not really have any elasticity, but they have a very high tensile strength. They have linear shape and they maintain side alignment and avoids and slipping of molecules. Some common examples I've written over here: cotton, wool, silk, which are natural fibers. Some synthetic fibers, we are going to prepare all of them: nylon, daceron, terylene and polyacrylonitrile or PAN. Next, very important, thermoplastic. Now, as the name suggests, students, thermoplastic, the main property that we have in these polymers is that you can, when you heat them, they soften on heating. So you can give them the required shape, and when they cool down, they harden. They go back, they get that hard, they become hard. So they can be molded into desired shape by heating, soften on heating, and then they harden on cooling at room temperature. Some examples are polythene, polystyrene and PVC. PVC, students, you would have heard PVC pipes, polyvinyl chloride pipes. Next, thermosetting. Thermoplastic polymers soften on heating and harden on cooling, but that property is not present in thermosetting polymers. So these polymers cannot be remolded or reused, you can say, on heating. Example is vulcanized rubber, bakelite. Bakelite is a very important thermosetting polymer, urea, formaldehyde, resins and so on. Now, there are certain plastics which do not soften on heating to a desired extent. They can be softened by adding some important organic compounds which are called as plasticizers. For example, dibutyl phthalate is used to soften PVC. The next is very important, the process of synthesis, how you convert a monomer to a polymer. So the first process that we have over here is called as addition polymerization, which is also called as chain growth polymerization. Now students, this is very similar to, many students would have done this in reaction mechanism, free radical mechanism. As the name suggests, chain growth. Now, there are very important 3 steps involved in chain growth polymerization, which we have: initiation, chain propagation and chain termination. So we will understand these in details, but let's just quickly go through the points. The formation of polymers by addition of monomers without the loss of any small unit, a small molecule, is called as addition polymerization, which is free radical mechanism. Now let's start by understanding what are the different steps taking place in free radical mechanism or addition polymerization. Chain initiation, or to initiate or to start the chain, we need a peroxide. An initiator such as benzoyl peroxide, acetyl peroxide, third butyl peroxide is used, and what we get here, students, it produces a free radical. So for example, we've used the alkyl peroxide over here, and it produces an alkyl radical. This is step one in initiating the chain. Now that alkyl radical will attack the monomer unit. In this case, we've used vinyl chloride, which produces a new radical. This is called as chain initiation. Now this new radical, students, will go and now attack another vinyl chloride molecule, and this process keeps on repeating. That is why it's called as chain propagation. So this keeps on repeating, repetition of this particular attacking sequence, and you get a long chain. That is called as chain propagation. Now, however, you need to terminate the chain, you need to stop this. And one of the most common methods, one of the common modes of chain termination is by combining the two growing chains. So the two growing chains, if you combine, that is finally, it stops the polymerization process. The next type of polymerization on the basis of the process of synthesis is condensation polymerization, which is also called as step growth polymerization. As the name suggests, step growth, what happens here is the process of formation of polymers from polyfunctional monomers, where we have, students, where we studied copolymers. What happens here is a small molecule, which can be water, it can be methanol, it can be HCl. So you remove a small unit from two different monomer unit, that is called as a condensation polymerization. So the process of formation of polymers from polyfunctional monomers with the elimination of some molecules such as water, HCl, small alcohol, methanol, ammonia, etc. is condensation polymerization. A common example is terylene. We will study the preparation of terylene. We'll come back to condensation polymerization over there. Similar to condensation polymerization, which is step growth polymerization, we have something called as ring opening polymerization. Students, more or less both are same, but in ring, both are step growth polymerization, but in ring opening, as the name suggests, you may have cyclic ethers, you may have cyclic esters, lactams. You open the chain and then polymerize. That's called as ring opening polymerization. We're going to study ring opening of epsilon caprolactam, which produces the polymer nylon 6. Now, students, I hope everyone is taking down all these points as notes. Now we move ahead to the next very important part, where we're going to prepare different important polymers. Let's start with the first polymer, where we have polythene or polyethylene. I am sure many students already know or have heard the word polythene. We've heard polythene bags. Now there are two types in this, students. One is LDPE, or also called as low density polythene. One is HDPE, high density polythene. As the name suggests, HDPE, high density polythene, will have a higher tensile strength, greater toughness, and what is important here is, students, you need to remember the catalysts, the temperatures over here. Ziegler-Natta is actually, though we say TiCl4 plus tetraethyl aluminate, Ziegler-Natta is an industrial measuring unit, though we'll not go in that detail. HDPE consists of linear chain polymer molecules having density Please remember the value. They are chemically inert, they have high tensile strength, greater toughness. Uses are very important. They're used for the manufacture of containers, pipes, bottles, toys, etc. On the other hand, LDPE or low density polythene, the reaction, the polymerization process remains the same. Please remember the conditions. Over here, traces of O2 or H2O2, that's your initiator. This consists of branch chain polymer molecules having lower density as compared to HDPE. Excuse me, they are chemically inert with moderate tensile strength and used in the manufacture of thin film sheets, insulators of wires and cables. LDPE is formed via free radical addition polymerization. Next, students, similar to polythene, where the monomer was ethylene, here the monomer is propene or propylene. So the polymer is called as polypropylene. It is the same method of preparation. However, it is prepared by passing propylene through hexane, which is your inert solvent containing Ziegler-Natta catalyst. That's your repeating unit. Basically, that's your polymer. It is harder, stronger, lighter than polythene, and it is used in ropes, carpets, packing of textile materials, so on and so forth. Next, we have people polystyrene, which I'm sure students have heard by the name Thermocol, and it is also called as Styrofoam. Styrofoam is usually used in the US. I mean the nomenclature, and we usually call this as Thermocol. Both, however, are the same. This is your polymer. This is your monomer styrene, which is your phenyl ethene. Benzoyl peroxide is your initiator, and this is your repeating unit, or that's your polymer. It's a white thermoplastic transparent material used in making combs, coils, ceiling tiles, TV cabinets, baggages, etc. The next polymer that we have, and I'm sure students have heard about this, which is Teflon. Students must have heard about Teflon coated pans or non-stick cookware. So the most important application of Teflon, also called as polytetrafluoroethylene, PTFE. So here you have tetrafluoroethylene, polymerization heating in the presence of ammonium persulfate, you get Teflon. And the most important application of Teflon, it is used in non-stick cookware, used for coating purposes. It's very tough and it is a poor conductor of electricity. uh, a slight you can say modification, we have something called as polymonochloro. So one of the F is replaced by Cl. Polymonochlorotrifluoroethylene, PCFE. It also has properties which is very similar to Teflon, however it is less resistant to heat and chemical. Moving ahead, the next important polymer that we have is called as PVC or polyvinyl chloride. Students must have heard about PVC cables. So the monomer that you have over here is your vinyl chloride or chloroethene polymerization process. We took the same example, students, when we were doing the polymerization process of addition polymerization. So it follows the same free radical mechanism. PVC is a hard material, but it can be made, using plasticizers. We had read the explanation for plasticizers, resistant to heat and chemicals. The most common use is PVC pipes. However, for raincoats, toys, electrical insulators, and so on. The next polymer that we have, students, and this is a rubber polymer, which is called as neoprene. Neoprene is, you can say, synthetic rubber which resembles natural rubber in properties. Students will study more about natural rubbers in the next in few slides after this. Natural rubber has to be, students, process which is called as vulcanization. We'll also study about vulcanization in this particular one shot. Neoprene is superior to rubber in oxidation and resistant to oil and solvents. The monomer that we have over here is, students, you can call it chloroprene, or you can call it as, it is the same as 2-chloro buta 1,3 diene. Polymerization takes place in the presence of a potassium persulfate, and this is your repeating unit or your neoprene. Uses: it is used for making shoe heels, stoppers, belts, etc. Next, we have students Buna-S, which we've already done, which was butadiene, styrene, and butadiene rubber. One more thing, however, important point you can remember is the ratio in which you take butadiene and which you take styrene, which is the ratio is 3:1. This is less tensile than natural rubber and is used in making tires, soles, and belts. The next polymer that we have is called as polyacrylate. Polymers obtained from the esters of acrylic acid, these are called as polyacrylate. So students are given the structure of acrylic acid, and this is the ester of polyacrylate. Pardon me, this is the ester of acrylic acid. Now this undergoes polymerization process, and this is your repeating unit, which are called as polyacrylates. We've taken an example, we've taken methyl methacrylate. So methyl methacrylate on polymerization becomes polymethyl methacrylate, which is PMMA, or we also call it as perpex or acrylic glass. And the most important application, students, it is used for making shatter resistant glass. Very, very important application. Moving ahead, we have PAN, or also called as polyacrylonitrile, acrylan or orlon. Now students, this is a substituent for wool. So we have PAN, or vinyl cyanide or acrylonitrile, which on polymerization becomes your polyacrylonitrile. And as written over here, polyacrylonitriles resembles wool and is used as a wool substitute. The next set of polymers we have, students, is called as polyamide polymers. Polyamide polymers have amide linkages, that's why they are called as poly, and many amide linkages, that's why polyamide polymers. The first one, very important, is nylon 6,6. Let's understand why the name has nylon 6,6. If we look at both the monomer units, the first one is adipic acid, first monomer, and the second monomer is hexamethylene diamine. Both the monomer units have 6 carbon each, and that is why the nomenclature is nylon 6,6. The name is nylon 6,6. And students, if you remember, we did condensation polymerization, where you remove a small molecule like water, like methanol. So we have nylon 6,6 is a condensation polyamide polymer, and it's also a condensation polymer, because if you see, we're removing H2O from each monomer unit, and this is, you can say, the intermediate nylon salt, which at 553 Kelvin under high pressure becomes your nylon 6,6. And here CONH is the amide linkage, which repeats, and that's why it's called as polyamide. Nylon has vast applications, has many applications. Some of the applications, students, there are many more applications. I've just written few, but you need to remember those polymers specifically, students, which have very unique uses. It's not that you should not remember the others, but just make sure, for example, something like a Teflon, or the wool substitute example. Now, just like we've done nylon 6,6, I want students to just try this question. If I give you something like nylon 610, so what will be the monomer unit? Pardon me, what will be the monomer for nylon 610? Please write the answer in the comment section. Next, students, we have a very important polymer, which is nylon 6, or also called as Perlon. Now students, we did this in the ring opening polymerization process, and after learning this, we'll also extend the reaction a bit, which is important for students preparing for the entrance exams. So the monomer that we have over here is epsilon caprolactam. This is epsilon, and when you heat it, you can see that the ring opens and you get nylon 6. It has high tensile strength, has luster, and used in the manufacture of tire cords, fabrics, etc. Now students, this epsilon caprolactam, I'm very sure that students have learned the preparation of epsilon caprolactam in reaction mechanism, and also in their class 12 organic chemistry. We'll understand how do you go from cyclohexane to nylon 6. Let's say if we have a question in, let's say in JEE Advanced, complete the reaction type questions, identify product, you can get a question like this. So from cyclohexane you can go to cyclohexyl chloride. Then from there we perform eliminate dehydrohalogenation. That gives you a cyclohexene, which on hydrolysis becomes a cyclohexanol, which on oxidation, so the secondary alcohol will turn into ketone. So you have a cyclohexanone. And then students, this reaction here is Beckmann's rearrangement. So cyclohexanone with NH2OH, which is hydroxylamine. Students would have done this reaction in aldehydes and ketones. That gives you oxime, and this particular oxime undergoes Beckmann's rearrangement. I'm sorry, though I've not explained the exact mechanism in between, since this is a one shot, we are short on time. But the oxime here gets converted into epsilon caprolactam, and then this epsilon caprolactam can become nylon 6 via the ring opening mechanism. Continuing ahead. The next polymer that we have, these are polyester. Just like polyamide had multiple amide linkages, polyester will have ester linkages. The example that we have over here is sterylene or Dacron. Again, students, this is a condensation polymerization. So you remove a small molecule like water. So we have ethylene glycol and we have terephthalic acid. Same thing, you'll be removing a very small, you will be removing water molecule. Sometimes methyl terephthalic is also used, and that produces terylene or Dacron. Terylene or Dacron is a good substitute for human blood vessels in operations. It has high melting point, it is resistant to chemicals, uses wrinkle-free fabric, terracotta, terrewool, glass reinforcing material into helmets. We have something called as polyethylene terephthalate, PET, which is the most common thermoplastic used for making packaging containers. I hope students can just quickly go through the theoretical point on their own. The reaction and the monomers are very important. Next we have students glyptal. Glyptal is again ethylene glycol. Now instead of terephthalic acid, which was there in the previous example, here we have phthalic acid. This gives you glyptal. Again, it's a condensation polymer obtained by removing water molecule. It uses paints and lacquer. Then we have polycarbonate. Polycarbonate is a monomer. The monomers are phosgene and bisphenol, and this is your polymer repeating unit used in electrical and telecommunication hardware and for making food grade plastic containers. Next, we have polymers which are based on phenol and formaldehyde. The first one, very important, we have bakelite. Before directly jumping into bakelite, students will first prepare a polymer called as novolac, and from novolac we'll move on to bakelite. The monomer units are, we have phenol and we have formaldehyde. So we get, students, over here, if you see, we get different products. You can say like ortho, para substituted products, out of which if you look at the ortho product, repeating unit and condensation of the ortho product produces what is called as novolac. You can say that they are joined at the ortho positions, and this is your novolac. Now students, novolac on heating undergoes cross linking to form an infusible solid mass which is called as bakelite. This is the structure of bakelite. Students, in your boards, you can have an independent question to just draw the structure of Bakelite. Uses are glass substitute, kitchenware, electrical insulators, and telephone instruments. Next, we have melamine formaldehyde polymer. So the monomer units are is we have melamine and we have formaldehyde. This is the intermediate, or you can say the resin intermediate, which is formed, which on heating again you can say that there is cross linking which takes place, and we have melamine formaldehyde polymer, which is also called as melamac. Now look at this, students, used in the manufacture of unbreakable crockery. So this is what I was talking about. Some of these polymers may have unique uses which they might particularly ask. Next, we have natural rubber. Natural rubber is a polymer of isoprene, which is 2-methyl buta 1,3 diene, and this is the actual structure. All the bonds are cis, so cis 1,4 isoprene. Natural occurring rubber in which all the bonds. There's also a natural occurring rubber which where the bonds are in trans, which is also known as gutta percha. Make sure you remember the structure for this. Now, in its natural form, students, we cannot really use rubber, so we need to modify it a bit, which is vulcanization of rubber. I think students have heard about Goodyear tires. It was actually done by a scientist Goodyear, and here in vulcanization, at temperatures greater than 335, natural rubber becomes soft, and less than 233 cold temperatures it becomes brittle. So we cannot really use it in its natural form. So what we do is we perform vulcanization. Natural rubber is insoluble in non-polar solvents and it is non-resistant to oxidizing agent. What do we do during vulcanization is natural rubber, raw rubber is heated with 5% of sulfur at about 373 to 415 Kelvin, and cross links are formed at relative sides of the double bond. Those students, we have mentioned that we use 5% of sulfur. It also actually depends upon what is the application going to be of that particular rubber polymer, and hence the amount of sulfur may vary depending upon, let's say, if you want to make a specific tire for a particular automobile, so on and so forth. But you can remember this, for this particular process, 5% sulfur at about 373 to 415 Kelvin, and cross linking takes place. Next, students, we have neoprene. Though we have already done neoprene, remember you can get questions like give a list of all the rubber polymers. Moving ahead, students, all the examples of polymers that we have done, though they are extremely useful, but they all have a drawback. They are a bit harmful to the environment. Some of them are very harmful because they don't really degrade over a long period of time. We know that pollution because of plastic, and hence we want biodegradable polymers, and we have a list of biodegradable polymers. So most synthetic polymers and plastics cannot be degraded by microbes, and they stay in the environment for a very long period of time, causing pollution problems. Aliphatic polyester and polyamides with very large proportion of polar linkages are one of the important classes of biodegradable polymers. Why are they biodegradable? Because they can be easily broken down into smaller segments by using enzymes, and these enzymes, they target that one particular hydrosable group, which is actually the weak link. Now the first biodegradable polymer that we have is called as PHBV. Let's understand that: polyhydroxybutyrate. So the first monomer is beta hydroxybutanoic acid, or 3-hydroxybutanoic acid, and beta hydroxyvalerate, it's a copolymer, which is beta hydroxyvaleric acid or 3-hydroxypentanoic acid. Again, a small molecule like H2O is removed. So this is also a condensation polymer. This is your repeating unit. Now, important applications. It is used in orthopedic devices. Basically, the capsule, students, that we have in the form of medicines, they usually come with a covering of PHBV. The next biodegradable polymer that we have is nylon 2, nylon 6. Again, as the name suggests, nylon 2, which means the monomer has two carbons. That monomer is glycine. Students would have learned this as the simplest amino acid. And we have epsilon amino caproic acid. Again, condensation, we are removing a water molecule. This gives us nylon 2, nylon 6, used in making strings of musical instruments, toothbrushes, etc. Another students, you can remember a very important biodegradable polymer, which is polyglycolic acid and polylactic acid, and these are actually used to make post-operative stitches. Finally, students, moving on to the last slide, molecular mass or degree of polymerization. Now, why students molecular mass of a polymer is very important. If a polymer, because a mass of polymer is nothing but the number of times that particular monomer unit has repeated. However, if your polymer has very low molecular mass, it can become brittle or probably has less tensile strength, low mechanical strength. However, on the other hand, if it has very high molecular mass, it can become tough and unmanageable. So there has to be a proper balance which is to be maintained in the molecular mass of the polymer. So molecular mass of a polymer is an average of the molecular mass of the constituent molecules, which depends on what is called as the degree of polymerization. A polymer must possess a molecular mass which should be balanced, not very low, not very high, and this is called as the critical degree of polymerization. Why is critical degree of polymerization important? For polymers containing hydrogen bonding, the critical degree of polymerization is lower than those containing weak intermolecular forces. Let's understand this. The critical degree of polymerization is low for nylon 6, but it is high for polythene. That tells us that polythene has weak intermolecular van der Waals forces, whereas there is hydrogen bonding in nylon 6. So I hope students, you enjoyed this one shot lecture on polymers. What you can do as a one shot, pardon me, to make short notes on polymers is, you can have a sheet where you have all the polymers, their units, their monomer units written, their general configuration of the repeating unit written, and uses, so that when you want to quickly revise, also you can add classification, whether they are polyester, they are polyamide, whether they are condensation, whether they are addition, and so on. So on a single page you can have like an entire chapter or the polymers written, so you can quickly revise probably 10 minutes before the exam. If you need such a sheet made, please let me know in the comment section. I'll make it for you students. And I hope you liked the video. Please like and subscribe to the channel, and thank you so much, students.